So this is the second video on the CC8 acids topic, which only comes up on paper 1. And in this video, we're going to take a closer look at how H plus concentration relates to pH. And we're going to have a look at strong and weak acids and concentrated and dilute acids. So just as a recap from the last video, we saw that acids produce H plus ions when they dissolve in solution. If you wanted to find out if something was an acid, you could get the pH. If the pH is less than 7, then it is an acid. To find that pH, you can use a pH meter or pH probe, or you can use an indicator, which is a substance that changes colour in an acid. So we saw that the acids have a pH of less than 7. So the pH scale runs from 0 to 14. If it's exactly 7, it's neutral, but anything less than 7 is acidic, and it runs the whole way down as far as 0. What's the difference though in the pH? Okay, if something's got a pH of 6, 6 is less than 7, so it's an acid. But if something has a pH of 0, again, it's less than 7, it's an acid. So they're both telling you that a substance is an acid. Why is there such a difference in the actual pH value itself? Well, if you've got a pH of just less than 7, so 4, 5, or 6, then your solution is only weakly acidic. If you've got a solution with a pH of 0, 1, or 2, or 3, then that solution is going to be strongly acidic. So basically, the further you're getting from 7, the more acidic it is becoming. And down here, with a pH of 7, that would be a solution that is strongly acidic. So we need to look at why. We need to look at what the difference is between acids with a pH of 0 and acids with a pH of 6. And we remember that all acids produce H+. So the difference in the pH does relate to the H+. And I've got a sentence here: the higher the concentration of H+, the lower the pH will be. So we said that as you move away from 7, it's getting more and more and more acidic. The reason it's getting more and more and more acidic is because it's got more and more H+. Remember, H+ is the ion that makes something acidic. As you're getting more and more acidic, you've got more and more H+. So the higher the concentration of H+, the lower the pH. Remember, the lower the number, the further away from 7, so the more acidic it is becoming. I've got another statement here. As the concentration of H+ ion decreases by a factor of 10, the pH will increase by 1. So that's quite maybe a confusing sentence. So we're just going to look at a diagram to illustrate what I mean by that. So I've drawn out a number of beakers. The beaker on the left has got 10,000 H+ ions. Then I've got 1,000 H+ ions, 100, 10, and then at the far right I've just got 1 H+ ion in there. Now they all contain H+ ions, so they are all going to be acids. They're all going to have a pH of less than 7. But which is going to have the lowest pH, which is the most acidic? Well, we've written here that the higher the concentration, the lower the pH. So out of all of my beakers, the beaker here on the far left has got the most H+. It's got the highest concentration of H+. So out of all of my beakers, it is going to have the lowest pH. It's going to be the most acidic. So I'm just going to assign this a value of pH 1. And I'm assigning this because it's the most acidic. It's got the lowest pH value because it is the most acidic. And the reason it's the most acidic is because it's got the most H+. It's got 10,000. So if I look at the beaker next to it, I've gone from 10,000 H+ to 1,000 H+. So what has happened is the concentration of H+ has decreased by a factor of 10. So you can clearly see that it's decreasing. You're going from 10,000 to 1,000, and it's decreasing by a factor of 10, because if I divide 10,000 by 10, I end up with 1,000. So it's decreasing by a factor of 10. If it decreases by a factor of 10, the pH of the solution will increase by 1. That means that this is going to be pH 2. Okay, the pH is increasing by 1 because the number of H+ ions has decreased by a factor of 10. If we look at the next beaker, I've gone from 1,000 H+ to just 100 H+. Again, I've divided by 10. So my H plus concentration is decreased by a factor of 10, meaning my pH is again going to rise by 1. I'm going from 100 H plus to 10 H plus. Again, it's decreasing by a factor of 10. My pH increases by 1. And then at the end, I've again diluted by a factor of 10. My pH increases by 1. So you will see as you move from left to right, you've got less and less and less H plus in the beaker. Because you've got less and less and less H plus, it's becoming less and less acidic. So that pH value is rising and it's getting closer to 7, which we remember is neutral. So here I would have the least acidic. And the reason it's the least acidic is because it's got the lowest amount of H plus. So as you decrease the concentration of H plus, that pH is rising, it's becoming less acidic, and the pH is getting closer to 7. Now obviously I just made all of these values up, because you may be asking yourself, well, it's pH of 5, if you decrease the concentration anymore, it's not going to be an acid, yet we're still nowhere near 7. So I did just make these numbers up to illustrate a point. I'm going to turn our attention now to alkalis. Acids produce H+, alkalis produce OH- ions in solution. And just like with acids, you can find the pH of an alkali using an indicator or a pH probe, and you'll see that they've got a pH above 7. So if I draw out my pH scale, everything above 7 is going to be alkaline. Remember, exactly 7 is neutral. Everything above 7 is going to be alkaline. It's going to have OH- ions. But just like with the acids, the further you get from 7, the more alkaline it will be. So if it's just slightly above 7, then it's going to only be weakly alkaline. It's not particularly alkaline. But the further we're getting from 7, up at the other end of the scale, that is when it becomes strongly alkaline. So with alkalis, the higher the pH, the more alkaline it is. So basically, if you're on either of the ends of the pH scale, either of the extremes, you've got the strongest acids here and then the most alkaline up here. So if I were to draw this out in just little beakers, I've got 3 alkalis here, and you can see they've all got OH- ions, and as I move from left to right, I've got more and more OH- ions. So if we wanted to assign pH values, they're all alkalis because they've got OH- ions, they're all going to be above 7. But which of these is going to be the most strongly alkaline? Well, the beaker here on the far right has got the most OH- ions, therefore the beaker on the far right will be the most strongly alkaline. Whereas over here, it's only weakly alkaline. And again, the reason for that, the more OH- ions, the more alkaline it's going to be. So if I wanted to give it pH values, we know they're all going to be above 7, but up here, the one that's strongly alkaline, I'm going to give it a pH value of 13. Whereas over here, something that's only weakly alkaline, I'm going to say it's got a pH value of 9. So I'm just making up these numbers again. Okay, it's just to demonstrate the fact that the more OH- ions you've got, the more alkaline it is, and the higher that pH value is going to be. In terms of what we did with acids, with you dilute by a factor of 10 and increase by 1, you don't need that for the alkalines. You just need to know that if you've got more, it's going to be more alkaline, and you're going to have a higher pH. So if we have a look at one or two worked examples, especially on these kind of pH questions. So it's saying here a solution of HCl has a pH of 1. So it's an acid, has a pH of 1. The solution is diluted by a factor of 10. What is the new pH? So if you're diluting the acid, you're going to be increasing the pH. You're going to be adding water to dilute it. If you're adding water, it's going to be getting less acidic, and that pH is going to be increasing. It's going to be getting closer to 7 because you're adding water to it. So I know my pH is going to increase, but if it's diluted by a factor of 10, then it increases by 1. If it starts off at pH 1, then it ends up at pH 2. The next question. Solution of HCl has a pH has pH of 2 this time. 10 centimeters cubed, so that's your volume, it's the same as 10 mils, is diluted to 100 mils. So you're diluting it by adding water. You're going from 10 mils of something to 100 mils by adding water. Okay? If you're diluting, again, remember, you're adding water, you are going to be increasing the pH. You're diluting by a factor of 10, so you increase by 1. pH of 2 becomes pH of 3. The last question is the opposite. You've got an acid with a pH of 3 and you've made it 10 times more concentrated and they want the new pH. If you're making something more concentrated, you're adding more H+, you're going to be making it more acidic. And if you're doing it 10 times, you are going to get a pH of 2. You're going to decrease that pH by 1. So we've seen the effect that H+ concentration has on pH. We're now going to have a look at the factors that will affect the amount of H+ you have got in an acid. So what we're first going to look at is strong acids and weak acids. So if you cast your mind back to that first video we looked at on acids, we saw that you took an acid, you took a substance, you dissolved it in water, and when it dissolved in water, the covalent bond broke and you ended up with 2 different ions, one of them being H+, which is why it is an acid. So this is a really important part of something being an acid. That bond has got to break. If that bond doesn't break, you're not going to get H+. In this example, I'm just going to use HA as a generic acid. Okay, HA is not the formula of an acid because A is not the symbol of any element on the periodic table. I'm just using it as a kind of generic representation of an acid. So here I'm saying that I've got 5 HA molecules, and I'm going to take my 5 HA molecules and I'm going to dissolve them in water. And because it's an acid, that bond between H and A is going to break, and when it does, I end up with H+ and I end up with A-, and I'm dissolving 5 of them and all 5 of them break. In my next example, I've also got 5 HA molecules. I'm going to take these 5 HA molecules, I'm going to dissolve them in water. But this time they are not all going to break. In some cases, that bond between H and A breaks and I end up with H+ and A- exactly as I have before. But in the other cases, that bond doesn't break and the HA stays together. The example on the left is what we call a strong acid, and it's called strong because it fully dissociates. Dissociates is just a kind of a fancier word for splits up. So you've got your HA molecule and it fully splits up. So I put 5 HA molecules in and every one of those HA molecule splits up. So I can say it fully dissociates, it fully splits up. On the right hand side, I've got what we call a weak acid and it only partially dissociates. So I put in 5 HA molecules and out of the 5, 2 of them split up, 3 of them did not. Again, dissociates means splits up. So I can say it's partially dissociated. I've got 2 out of 5. So that's a strong acid, fully splits up. A weak acid only partially dissociates. But now we need to have a look at how this is going to affect pH. Well, we know that H+ ions are what make something an acid. And on the acid here on the left, I've got 5 H+ ions, whereas here on the left I've got 5, whereas on the right I've only got 2 H+ ions. So they are both acids, but which one is more acidic? Well, it's going to be this acid here on the left that is more acidic. It's more acidic because it's got more H+. Okay, it's the H+ you're counting, not just the HA. It's got more H+, therefore it's more acidic. If it's more acidic with more H+, is it going to have a higher or a lower pH than the acid here on the right? It's going to have a lower pH. Remember, the more H+, the lower that pH is going to be. So let's just say this is going to be pH 3, and we'll call this one over here pH. I haven't diluted by a factor of 10, so I'm just going to call it pH 3.5. I'm just going to make it a bit higher, okay? Again, I'm just making these numbers up, all right? But the more H plus it's got, the more acidic it's going to be, the lower the pH. An acid that fully splits up, so a strong acid is going to produce more H plus than a weak acid will. The other thing we need to consider is concentration, and concentration and strength in chemistry are not the same thing. So we've already seen what we mean by a strong acid and a weak acid. Now we're going to look at what we mean by a concentrated acid and a dilute acid. So if an acid is concentrated, it's got a high number of acid molecules dissolved in solution. If it's dilute, it doesn't have a lot of acid molecules dissolved. And again, this is easiest if we just look at examples. So I've got 4 examples of acids here. Okay, and again, I'm just using HA to represent an acid. We're going to go through each of the 4 pictures and we're going to classify them as concentrated or dilute. So the first one here on the left, remember concentrated, you've got a high number of acid molecules, dilute, you've got a low number. So if we just do this comparatively, we can see that over here on the left, you've got a high number of acid molecules. You've got lots of HAs in there, so I can say that this is concentrated. The next one over is again going to be concentrated, but then the 2 on the end are going to be dilute. So that's just the difference between concentrated and dilute. It's just the amount of acid molecules that you've got. These 2 packed full of HA, these 2 not so much. Concentrated, dilute. But now we're also going to look at strong and weak, which we've just looked at before. So this is my concentrated acid. Is it strong or is it weak? Well, if we look at our HA molecules, you can see that most of them have stayed as HA. Only one has actually split up to give you H plus and A minus. That means it's only partially dissociating and it means it is weak. The next example, on the other hand, every single HA molecule has split up to give you H plus and A minus. So it is fully dissociated. It is strong. The next one over, you have got 1, 2, 3, 4 acid molecules. 3 of them have not split up. 1 of them has split up. So again, it's only partially dissociated. It is weak. And then at the end, you have got 2 acid molecules in total. Both of those acid molecules have split up. Therefore, it is fully dissociated and it is strong. So we're just going to link these ideas, strong, weak, concentrated, dilute, back to pH. And what we saw in the first example was our strong acid had a lower pH than the weak acid because our strong acid was more acidic. But is that always the case? Do strong acids always have a lower pH than weak acids? Well, when they have an equal concentration, then the answer is going to be yes. So here, I can say they've got an equal concentration because they've each got 5 HA molecules. Because this acid is strong, it produces more H plus than my weak acid when the concentrations are equal. But if we look at another example, which I'm going to do up here, this time I do not have equal concentrations. Of my strong acid, I have only got 2 molecules. But in my weak acid, I have got 20 HA molecules. So again, if my acid is strong, then it's going to fully dissociate. I'm only putting in 2 HA molecules, but they will both split up to give me H plus and A minus. In my weak acid, I'm not going to draw out 20, but in my weak acid, they're not going to fully dissociate. So let's just say that a quarter of your acid molecules are going to dissociate, which means 5 out of your 20 HA molecules will split up, the other 15 won't. If 5 of them are splitting up, H plus A minus, H plus A minus, H plus A minus, H plus A minus, 5 of them are splitting up, and then the other 15, and I'm not going to draw 15, but the other 15 are going to remain as just HA. Because it's not fully dissociating, it is a weak acid. But because it's so much more concentrated, if you look at the H plus, because it's more concentrated, you end up with more H plus ions in your weak acid than you did in your strong acid. So if you have a situation where your weak acid is more concentrated, you can have a situation where you've got more H plus ions in your weak acid. Okay, remember it's weak, it's only partially dissociating, only 5 of the 20 have split up, but that's still more than the 2 HA molecules that split up in your strong acid. So if we have a look here at an example, okay, so how can a weak acid have a lower pH than a strong acid? So remember, if they're asking you about it having a lower pH, that must mean that your weak acid is more acidic than your strong acid. How can that be the case? Okay, if you want something to have a low pH, it must have a high concentration of H plus ions. I then define what a weak acid is. So weak acids do not fully dissociate, so do not produce a lot of H plus ions. Strong acids do dissociate, so do produce lots of H plus ions. Okay, so this would suggest that your strong acid would have a lower pH. However, if the weak acid was concentrated and the strong acid was dilute, the weak acid could have more H plus ions in solution and hence a lower pH. So what you really need to have here is you need to have your definition for a weak acid and your definition for a strong acid. That's 2 out of the 4 marks by just defining what they are. Then you need to link pH to H plus concentration. So you need to say that even though your your weak acid is not fully dissociated, that if it's concentrated, it can have more H plus than the strong acid and therefore a lower pH. So you have to mention H plus. You have to mention the fact that your weak acid, if concentrated, can have more H plus ions and therefore a lower pH. I'm going to get you to do a few questions. So these ones are slightly harder. So section B. So just do questions 1, 2, 3, 4, and 5 from section B. Press pause, have a go, and then press play when you're ready to see the answers. Okay, so I've done the answers out here. The ionic equation, we had that in the last video. H plus and OH minus goes to H2O. That is the easiest 3 marks you'll ever get. An acid pH of 2 diluted by a factor of 10. It now has a pH of 3. Remember, you're increasing that pH because you're adding water. You're going to be getting closer to 7. Student has 10 centimeter cubed of an acid with a pH of 1. You're adding water until the volume is 100. So you're diluting by a factor of 10. Okay, if you're adding water, you're going to be increasing that pH. You're diluted by a factor of 10, you increase by 1. A student had 2 acids that have the same concentration. One was weak, one was strong. Why does the strong acid have a lower pH than the weak acid? Okay, so again, give the definition of weak and strong. That's going to be your 2 marks. So weak acids do not fully dissociate, strong acids do fully dissociate. That means that strong acids are going to produce more H plus ions and lead to a lower pH. So you get 1 mark for your definition of weak, 1 mark for your definition of strong, and your 3rd mark goes for linking the amount of H plus ions to that pH. How can a strong acid be less corrosive than a weak acid? So I've given you a hint here. If something's less corrosive, it means it's less acidic. So you're explaining why the strong acid is less acidic than your weak acid, which is the example that we looked at before. So again, I've started by just giving the definitions of weak and strong. However, if the weak acid is concentrated and the strong acid is dilute, then the weak acid can produce more H plus ions and therefore is going to be more acidic. So a mark for your definitions. Then you need to mention that the weak acid might be concentrated while the strong is dilute, and then you need to be mentioning H plus ions. If it's concentrated, it could have more H plus ions. That makes it more acidic and therefore more corrosive. So in the next video, we're going to have a look at reactions of acids. We're going to look at neutralization reactions when we react them with bases. We're also going to look at the reactions when we react acids with metals.